The last decade has seen prolific development of quantum technologies that have the potential to profoundly transform computing, communications, and sensing by harnessing the laws of quantum mechanics. This isn't just a futuristic dream. Small-scale prototype quantum computers have been built by companies like IBM, Google, IonQ, and Quantinuum. There are also extremely sensitive magnetic field sensors using diamonds, and you can now buy a commercial quantum key distribution system. Despite all this progress, there's still a huge amount of work left to do to scale up these technologies to the point that they can do things that are economically relevant. While it's possible that existing technology platforms will eventually reach that point, our belief is that the giant leap that is still needed will come from new materials with more robust quantum effects. This will allow existing quantum technologies to reach new levels of capability and also realize entirely new quantum technologies. At the MonArk NSF Quantum Foundry, we're convinced that atomically thin 2D materials hold the key to many of those breakthroughs. MonArk is an effort led by Montana State University and the University of Arkansas to develop a nationwide solution to the challenges of creating and using 2D materials and to accelerate the pace of their development for quantum technologies.
So 2D materials refer to a special class of bulk crystals that consist of millions of atomic sheets that are stacked on top of one another. In these bulk crystals, the bonds between the atoms within a sheet are much stronger than the bonds between the atoms in adjacent sheets. This difference in bond strengths enables researchers to peel or mechanically exfoliate a single atomic sheet from the bulk crystal to obtain a true two-dimensional material system. There are many reasons that scientists and engineers are excited by these atomic sheets. First, thousands of 2D materials are predicted to exist. They exhibit all known behaviors such as superconductivity, magnetism, electrical conductivity, and beyond, but in a truly 2D limit that is difficult or impossible to reach with non-2D materials. And because they are atomically thin, their physical properties are dominated by quantum effects. They are inherently quantum systems. Over the last 10 years, researchers have demonstrated the ability to reassemble these atomic sheets with one another to build high-tech materials with greater functionalities, one layer at a time. Being able to stack different 2D atomic sheets on top of one another provides an extraordinary and unprecedented versatility to engineer new materials at the atomic level, especially for quantum technologies. Currently, the majority of 2D quantum materials research has been achieved by assembling these advanced systems using painstaking manual processes.
I am currently engaged in the preparation of 2D material samples. This process includes manually exfoliating 2D crystals down to atomically thin layers, which are subsequently stacked to make a quantum device. Currently, this process is done manually, and it's repetitive, labor-intensive, and time-consuming. The process yields are very low and involve large variability. Being a part of MonArk, I am excited to see the development of 2D fabrication pipelines addressing some of the limitations of conventional methods, allowing students and researchers to spend more time on exploring physics and other creative activities.
A major component of MonArk is the development of 2D quantum materials pipelines to speed up and improve the quality of the fabrication of quantum devices made from 2D materials. These pipelines exploit robots to perform the key steps to build the quantum device from exfoliation, flake hunting, and stacking the atomic sheets together. These multi-layer 2D stacks are transformed from samples into devices using state-of-the-art micro and nano fabrication processes. To produce highest quality devices, all these processes are executed in extremely clean environments to minimize or eliminate exposure to contaminants. The pipelines leverage advances in robotics as well as artificial intelligence and machine learning to increase the yield and quality of the samples. They are versatile and designed to work with a broad range of 2D materials and device architectures. Complementing the pipelines, the MonArk also offers an extensive suite of quantum and nanoscale characterization infrastructure designed to rapidly perform quantum experiments, which often requires deep cryogenic temperatures, ultra-fast timescales, and high magnetic fields. By combining the pipelines with characterization infrastructure, MonArk is a one-stop shop for two-dimensional quantum materials research.
Several scientific teams at MonArk are pursuing major research projects to discover and exploit unique properties of 2D materials for quantum technologies. These scientific teams are composed of professors, grad students, undergrad students, professional engineers and researchers, and even high school students. Many of our teams involve researchers from more than one of our partner institutions. The research activities of these teams span 5 main areas: the investigation of ferroelectricity in 2D materials, 2D magnetism, 2D qubits, 2D semiconductors for quantum photonics, and the development of advanced fabrication techniques for 2D quantum devices. The first major research area is the discovery and investigation of ferroelectricity in 2D materials. In fact, we were early leaders in this field. These materials change their physical properties in unusual ways. They can also be used to manipulate light. In the two-dimensional limit, exotic but useful electronic properties are also predicted to emerge. All of these properties have strong potential for applications such as stable quantum bits and optical entanglement sources in quantum photonics. Many participants in MonArk are working to understand, grow, and apply 2D ferroelectrics to these quantum applications. The second major research area is the study of magnetism in 2D materials, which also behave differently than they do in 3 dimensions. MonArk researchers contribute to the theoretical understanding of this behavior and also to controlling or modifying that behavior by growing new crystals that have not been synthesized before. The third research area is the development of new quantum bits known as qubits, based on 2D materials. Qubits are the fundamental building blocks of quantum computers and quantum communication systems. In many ways, qubits are the quantum equivalent to bits in conventional computers. Many 2D systems have novel degrees of freedom that promise better and smaller qubits than those we have today. The fourth major research area is the development of 2D materials for quantum photonic technologies, where light is used to transport and process quantum information. MonArk research teams are intensely pursuing 2D semiconductors to create quantum states of light and to build multi-layer systems to process those states of light as well. Many of these projects involve research partners from industry. And finally, the fifth research area is the development of the technologies of the so-called fabrication pipelines. Many teams are focused on the development of the robots and processes of those pipelines, all of which are research projects in themselves.
This experience has gone beyond a typical educational journey. It's been an incredible opportunity to immerse myself in the world of quantum materials research. The collaborative environment here allows us to work alongside leading researchers who explore groundbreaking technologies and contribute to innovations that build the future. MonArk provides a unique platform to bridge theoretical knowledge with hands-on experience, offering various possibilities for aspiring researchers like myself. Whether it's exploring 2D quantum materials or pushing the limits of quantum technologies, this chance is more than just learning. It's about actively shaping the future of science.
The MonArk Foundry is striving to have a broader impact beyond the exciting research that is happening at our founding institutions. We have expanded our initial partnerships to include the University of Arkansas at Pine Bluff, South Dakota School of Mines and Technology, and San Diego State University. The United States presently and desperately needs a diverse workforce to support the rapidly growing industries in quantum materials and technologies. This workforce will be essential to maintain U.S. leadership in quantum technologies, which is important for taking advantage of economic opportunities and supporting national security. The emerging quantum industry needs scientists, engineers, technicians, and business strategists. We are proud to contribute to solving this workforce development need by having students and educators at the K-12, undergraduate, and graduate levels participating in the research at MonArk.
The MonArk Quantum Foundry has also had a significant impact on the regions of its founding institutions. In Montana, MonArk has contributed to several university-to-industry economic development initiatives that are aimed at expanding the regional excellence in optics and photonics to the emerging areas of quantum technologies.
In Arkansas, relationships formed through MonArk led to a National Science Foundation project that brings quantum research and education to the University of Arkansas Pine Bluff. Finally, MonArk is working to form a national network of quantum researchers and engineers from academia, industry, and national labs. To fulfill that aspect of our mission, the facilities, including the pipelines and our characterization infrastructure, are available to quantum materials researchers through a collaborative research program. The MonArk team is eager to train and collaborate with external researchers. We want to put the pipelines to work, preparing samples and prototype quantum devices to facilitate and enable their experiments. We need all kinds of people to work with us, not just people who are working on a doctorate degree, but we need people with 2 degrees, associate degrees, people with a bachelor's degree. That's where most of the jobs in the quantum industry are going to show up. We're at the frontier of science. We don't know what we're going to find, but we don't know what is possible either.